All right, 895. Calculate the mass percent of a solution that contains 19 grams of sodium sulfate and 72 grams of water. Well, whenever you do mass percent, it's always going to be part over whole times 100. So your part is 19 grams of sodium sulfate, and your whole is the 19 grams of sodium sulfate plus the 72 grams of your water times 100, and that is going to give you 20.879% or 20.9%. Just misses being old enough to drink. That's that for that one. Let's take a look at another one. All right, let's take a look at 897. What is the molarity of a solution that contains 8 grams of sodium hydroxide in 700 milliliters of solution? Remember, molarity, by definition, is moles of solute per liter of solution. So we've got 8 grams of sodium hydroxide over 700 milliliters of our sodium hydroxide solution. So now it's just a matter of doing some quick unit conversions. Let's take care of the milliliters first. We have milliliters down the bottom. We're going to place them where they cancel out. We want liters. 1 milliliter is 10 to the negative third liters. So now we've gotten rid of milliliters. We've got grams over milliliters. We now have grams over liters. We now need to get rid of grams. Even though my grams are over here, multiplication is commutative, so I can still cancel them out all the way over here. I want to go from grams of sodium hydroxide to moles of sodium hydroxide. So I'm going to run to my periodic table. All right, so 22.9897 plus 15.9994 plus 1.00794 gives you a mass of sodium hydroxide of roughly 39.997 grams of sodium hydroxide, moles sodium hydroxide. Hey, we now have canceled out those grams, and we have units of moles per liter, or molarity. So now it's just a matter of multiplying everything on top, dividing through by everything on the bottom. And when you do that, you get 0. Looks like we're looking at 2 sig figs here, 0.2857 or 0.29 molarity. All right, let's take a look at another. 9.94. Answer the following. How many grams of lead-2 chloride will be formed from 52 milliliters of a 1.7 molar potassium chloride solution? You've got 2 numbers here. Can we identify one of these 2 as a conversion factor? Yeah. One of the things I told you in lecture was that molarity can always be viewed as a conversion factor that relates the number of moles of the substance to 1,000 milliliters. So that's a conversion factor. So that means our other number is what we're going to start our line with. So we're going to start our line with 52 milliliters of potassium chloride. We don't want milliliters of potassium chloride, so we're going to go to moles of potassium chloride. Remember, molarity is the world's greatest conversion factor because it lets us go from milliliters to moles, right? There's our equality statement based on that number right there. That tells us we have 1,000 milliliters per 1.70 moles. So now we have moles of potassium chloride. We don't want moles of potassium chloride, so we have to get rid of them. We're wanting moles of lead 2 chloride. That's where our chemical equation comes in. It lets us switch between two substances. Oops, I circled the wrong two substances there, didn't I? It tells us our relationship between potassium chloride and lead 2 chloride. It tells us that we need 2 moles of potassium chloride for every 1 mole of lead 2 chloride that we're going to produce. So now we have moles of lead 2 chloride. Now we just need grams of lead 2 chloride, no problem. You guys have been doing molar mass for so long. You're practically doing it in your sleep. So you're going to run to the periodic table and look up that molar mass. That gives us 278.1 grams of lead 2 chloride per 1 mole of lead 2 chloride. So now we've canceled out our moles. We have units of grams, which is what we're looking for. So now we multiply everything on top, divide through by everything on the bottom. And that gives me 12.29 grams or 12.3 grams of my lead 2 chloride. That's it for that one. 950. 950 is a great stoichiometry problem involving molarity. Now, we've got 3 numbers. Can we identify any of them as unit conversions? Yeah. Whenever you see a molarity, that's a conversion factor. That relates milliliters, 1,000 milliliters of sodium hydroxide as being equivalent to 0.200 moles of sodium hydroxide. Then we've got another one down here. The molarity relates milliliters, again, 1,000 milliliters of nickel 2 chloride being the same thing as 0.350 moles of nickel 2 chloride. So we have 2 conversion factors. We're not going to start with either of those. That leaves us with one number, that 20 milliliters. So that's what we're going to start our line with. So I've got 20 milliliters of nickel 2 chloride. The only thing I ever know how to do with milliliters is to get rid of them. So I place milliliters where they cancel out. A 1,000 milliliters is equivalent to 0.350 moles of nickel 2 chloride. So now I've canceled out my milliliters. Thing is, I'm not interested in nickel 2 chloride. I'm interested in sodium hydroxide. So I need to place my moles of nickel chloride where they cancel out. In order to switch substances, remember, we need a chemical equation. This chemical equation says that for every 1 mole of nickel 2 chloride we have. We're going to produce 2 mole. We need 2 moles of sodium hydroxide to react with it. So 1 mole to 2 moles of sodium hydroxide. I have moles of sodium hydroxide. Now I'm going to place those moles of sodium hydroxide where they cancel out, because I'm not wanting moles. No, I'm not wanting moles. I'm wanting milliliters. Do I know a relationship between milliliters and moles? Yeah, right up here. It tells me that 0.200 moles of sodium hydroxide are equivalent to 1,000 milliliters of sodium hydroxide. So now I've canceled out my moles of sodium hydroxide. So I have the units I'm wanting. So it's multiplying everything on top, dividing through by everything on the bottom. And I get $70 milliliters of sodium hydroxide. All right, that's that for that one. I think this one's one of the harder ones for this class. Acetic acid is an acid that completely disassociates in water. Given that the equilibrium concentration of this, what is the concentration of the acetic acid? And that the concentration of acetic acid is 0.6 and the acetate ion is 0.9 molar, what is the concentration of the hydrogen ion? Well, remember, your equilibrium constant is products over reactants. So, setting it up symbolically, products over a reactant see if it'll let me move that. Yeah, it'll good. Moving it down here where it's a little bit more convenient. And they've told us in the problem that this is equal to 1.8 times 10 to the negative fifth. They then tell us that the concentration of acetic acid is 0.16. So there's your acetic acid. They've told us the concentration of the acetate ion is 0.92. And they want us to solve for that hydrogen ion. So now it's just algebra. And you undo you do your algebra, and you wind up with 1.8 exponent negative 5 times 0.016 divide by 0.92, and that gives you 3.1 times 10 to the negative 7th molar as your concentration of your hydrogen ion. Oh, which is barely large enough to be that of water. Yeah, that's right. Okie dokie, Bert. Let's take a look at the next one.